on Zoom. I'm going to put the lab up on the Google Drive here in a minute. It should be on Blackboard, is it not? Yeah, under 132. I don't know if I put it on 131, but in ElectS 132 on the announcements, there's an announcement that says Lab Zoom ID, and that should have went to your email too. Oh, it's on the Google Drive too. Yeah, when you come in here, I just get on Google Drive and Zoom because I'm cool like that. You know what I'm saying? Is everybody here? No. That's all right. We'll start anyway. What the hell? Right? Can I get an amen?
Amen.
Amen. Oh, I love you guys. There he is. Now we can start. Just kidding. We haven't even started yet. What am I doing? Oh, lab. All right, you should see lab 3. Right yonder. Y'all got it open? So it looks like we're going to need a 150 ohm, a 270 ohm, and a 330 ohm. Gavin's got a thumbs up. Man, somebody even put the colors on there for you. What a nice guy that guy is. Daddy, you missed the important question. Did you get arrested this weekend? Damn. One of these days. An electronic circuit is a complete path through which electrons can flow from the voltage source through the connecting wires and load device and back to the source. The circuit is arranged so that electrons have only one possible path. The circuit is called a series circuit. Therefore, a series circuit is defined as a circuit with only one path for current flow. One of the most important aspects of a series circuit in relation to current flow. The amount of current in a series circuit will be the same value at any point, right? Series circuit, current's the same everywhere, as defined by Ohm's law. Another interesting aspect of series circuits is shown in voltage. The applied voltage is dropped proportionally across individual resistances, depending upon their resistance value, and the sum of these individual voltage drops will equal the amount of applied voltage. For this reason, the series circuit is sometimes referred to as a voltage divider. Now, we got into this a little bit in Thursday's lab. We didn't test voltage drop, but we knew that current would be the same throughout the whole circuit, right? So you had same amount of resistances across those three resistors, but they could only handle a certain amount of wattage per resistor, right? So that's why it was important to see same resistance, bigger wattage resistors can handle that same amount of current. Anyway, here's a procedure. With an ohm meter, measure the value of each resistor and record their values in table 1. I'm going to skip that part and just assume that my resistor is... No, I won't skip that part. I'll do it with you guys. How about that? What do I need? 150, 270, and 330. Where's the damn brown, green, brown one? There's one.
Where's the orange brown one? Huh? I don't have a bag, I have a cup. Oh. Boom. Resistor 1. Y'all remember how to set up your meter for resistance? Who keeps stealing my minute grabber? Huh?
I said probably Tom.
Damn it, Tom. Oh, I did. I left them up here. Still oh, Tom. When in doubt, it's Tom's fault.
Why blame yourself when you blame somebody else?
Exactly. See? We're going to go on just fine. All right. Well, if you need me to show you how to get set up for resistance on your bench meter, let me know. Otherwise, I'm just going to assume that you are with me. All right. So I got me a 149.19er. Got 269.75er. And I got a 328.26er. So how do we find the total resistance in a series circuit? Add them all up. Who said that? Nice job. Did you learn that yesterday?
Yes, sir.
That's what I'm talking about. Man, that's Steve. He's a good teacher. He's an ugly son of a bitch, but he's a good teacher. I hope he never watches these YouTube videos. So I got 149.21, 269.75, 328.26, 747 point, what was it? 22. Boom. So what is the voltage going to be at resistor 1? Point A.
Say no,
10. How do you know?
because that's what's coming out of the power supply.
Right. So, first thing we got to understand is you guys talk about electron current flow versus conventional versus, right? Yeah. So how do we know which side the power supply is going to be plus and minus? Or in your power supply, is that they're labeled red and black, plus and minus? Is that conventional current flow theory, or is that electron current flow? That's conventional. Just like your car battery, they're saying that there's a positive charge on the plus, and current's going to flow from positive to negative. When in reality, if we could get a microscope or something and watch the electrons flow, they're actually going opposite, right? So they mislabeled their battery, their terminals. It doesn't matter. It's just understanding that there's a positive charge and a negative charge relative to each other. Okay, so if we do our calculations with blow this up. If we do our calculations with, how do I, this being plus and this being minus, and we hook it up and we're not getting the right values and polarities reversed, how are we going to solve that? We're just going to switch the leads, right? Not a big deal. Right now, we're just trying to look at voltage drop. Okay, so if mine, and I'm going to do the first one for you, but like Tegan was saying, right? Voltage here is going to be plus 10. Because none of these resistors are consuming any of that voltage yet. So how do we go about figuring out what the what the voltage at point B will be? Also remember that when we're taking voltages here, where are we going to put our leads? Our black lead is going to be here, right? And our red lead is going to be wherever we're taking voltage at. So point A, you're basically just reading across the power supply. Or if that was a battery, you'd just be reading the voltage of the battery. At point B, we're going to put our lead somewhere between the two resistors. So what do we think that value is going to be? Which thing? Remember we said that if these were all 150 ohm resistors, that voltage would distribute evenly, right? So less resistance is gonna consume less voltage than more resistance. So here's how I think of it. I think of it in terms of a percentage, right? We know the total resistance right here, 747.22. So what percentage is this resistor going to eat up of the voltage? My value is 149.21. How do I find a percentage of the total with those numbers? Come on, math whizzes.
Divide the smaller number
Yeah.
by the bigger number.
Take take my measured value divided by the total resistance. So 149.21, that's my number. Your number's probably different. Divided by 747.22. And that gives me, whoops. That gives me 19.97%. So now what do I need to do?
Multiply that by voltage.
Right. If I want to know how much voltage this thing's going to eat up, I'd multiply that times voltage. So 0.1997 times 10 equals 1 basically 1 or 2.0, but it's 1.997 volts. So my resistor number one is going to eat up 1.997 volts. If that's the case, what value could I expect at B? Whoops. Any guesses? Yeah, 10 minus that. So at B, I could expect to read 8.003 volts. Does that make sense to everybody? Because that's the example I'm going to give to you. Let me see. VR1, VR2, VR3, I total. Current at point A, current at point B, current at point C. All right, so my calculated value for voltage across R1 where are they wanting current at point A, current at point B, current at point C? I guess I'm wanting you to do this lab different than the lab is actually saying. So let's back up. Voltage across R1. Oh, I see what, okay. So this is not I apologize. This is not voltage drop. It's saying resistance total. What was mine? 747.22. So what is the current going to be? If I know that 10 volts is the total voltage, I know my R total is 747.22. I total would be, what was it?
13.3 million.
So theoretically, is that current the same as across all those resistors? Yes. I thought, apparently Zach thought we were doing a voltage drop lab and we're not. We'll do that later. So here's what we're measuring. Red lead, black lead across R1. So at R1, what is my current? $13.38 milliamps. So I'm going to put it as 0.01338 amps. My resistance value at R1 is 149.21. Ohms. So what's my voltage there? E equals I times R. No, Steve was calling the bookstore.
Is that what he's gonna do? I
Yeah.
read that email, I wasn't sure, because the one kid was saying something about the board. I was like, I don't know.
Could be. Did Steve talk to you guys yesterday about your meters coming from the bookstore?
Oh, he did say something, okay.
September 4th, they what?
They have the tools and everything at the bookstore.
Are they giving you a discount?
I don't know, he said
They should.
He said he
Jeez.
was infuriated.
That's like a fourth plus of the semester that you guys didn't have your meters. All right, E equals I times R, 149.21 times hey, look at that. Same value, 1.9, basically 2 volts. Now when I measure across R1, I should see 2 volts. So current at resistor 2 is going to be the same, right? I equals 0.01338 amps. So the voltage drop there should be whatever you come up with. R3, current's going to be the same. I equals 0.01338 amps. So the voltage drop there is going to be a little different. Then you're going to measure
across each resistor to see what your actual voltage drop is. I'm going to switch for a second. And show you guys how I'm going to set this circuit up. So this is going to be my plus 10 volts. This is going to be my common. And my first resistor is 150. So I'm going to go plus. And then I'm going to go series with this resistor. And then I'm going to complete the circuit with my last resistor. Then with my meter, I'm reading voltage. How do I read across resistor 1? Where do I put my leads? Across resistor 1. See what I'm saying? And then what I should read there for voltage is 2 volts. Make sense? So I'd go through and do all your calculations first and then go through and read your volts. So we need to read voltage across resistor 1, voltage across resistor 2, voltage across resistor 3, and total current. How can we read total current? Why don't I give you time to get your voltage readings done, and then we'll go through that together. Because you guys are like the quiet people ever this morning. M Daddy, I like your name on there. That's what I'm talking about. You hated it the first day. Now you're loving it. You're rolling with it. You're walking across campus and all the chicks are like, hey, who's that? It's M Daddy. Mic drop. I love it.